we now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in December 2023. The problem is related to the properties of real symmetric matrices from the section Linear Algebra. This question is from the part C for 4.75 marks, and it is a multiple select question. There can be more than one answer in the options. The question bears a ID as 704075. The given question is, let A be an n by n real symmetric matrix. Which of the following statements are true, are necessarily true? We are given four options. Option 1, A is diagonalizable. Option 2, if a power k is equal to identity for some positive integer k, then a square is equal to identity. Option 3, if a power k is the zero matrix for some positive integer k, then a square is equal to the zero matrix. Option 4, all eigenvalues of A are real. Let's now discuss the solution of the problem in detail. We have capital A, an n by n real symmetric matrix. Agreed. So, to answer this question, you must be familiar with the properties of real symmetric matrices. We consider options 1 and option 4. Option 1 is A is diagonalizable. Option 4 is all eigenvalues of A are real. These are the two important properties of a real symmetric matrix. We recall what are those properties. We have every real symmetric matrix is diagonalizable and all eigenvalues of a real symmetric matrix are real. These are two important properties and the theorems related to real symmetric matrices. Right. So from this, it's very clear. Option 1 is true. Option 4 is also true. So option 1 is true and option 4 is true. Let's move to the third option. If A power k is the zero matrix for some positive integer k, then A square is also equal to 0. Right. So first of all, we have A is an n by n real symmetric matrix, and it is given A power k is equal to 0 for some positive integer k. A power k is a zero matrix for some positive integer k, means A is a nilpotent matrix. Thus, A is a n by n real symmetric nilpotent matrix. And recall the result that A is 0. How? The result what we are using is, because the only nilpotent real symmetric matrix is zero matrix. It is a real symmetric matrix and it is nilpotent. And if he is nilpotent and a real symmetric matrix, who is he? He is the zero matrix only. Because this is the result. The only nilpotent real symmetric matrix is the zero matrix. So A is 0. When A is 0, A square is also a zero matrix. So from this, A is 0 will imply A square is also the zero matrix. Hence, you get the conclusion of the option 3. Option 3. So thus, the option 3 is also true. So Thus, so far, option 1, option 3, option 4 are all the three are true. We are left with the second option that we will discuss in the next slide. Right. Your second option is if a power k is identity for some positive integer k, then a square is equal to identity. So, first of all, we have capital A, an n by n real symmetric matrix, and every real symmetric matrix is diagonalizable, therefore it is diagonalizable. Now recall a result about the diagonalizable matrices. The result is A is diagonalizable if and only if its minimal polynomial is a product of distinct monic linear factors. Monic means the degree of the polynomial is 1. Linear factors means something ax plus b type, and monic means x plus a type. Monic linear factors means it is of the type x plus a. Right. A is a real symmetric matrix, therefore it is diagonalizable. Recall a result. A is diagonalizable if and only if its minimal polynomial is a product of distinct monic linear factors. Right. Now let us take a power k is equal to identity. It is given to us. A power k is identity means A satisfies the polynomial x to the power of k minus 1. That means x power k minus 1 is an annihilating polynomial for A. And recall, it is known, the minimal polynomial m a of x always divides the characteristic polynomial and annihilating polynomial. Now, the minimal polynomial m a of x must divide the annihilating polynomial, that is x to the power of k minus 1. Now, we discuss from now onwards in two cases. The first case when k is odd, the second case when k is even. So, the first case when k is odd, and the minimal polynomial is a product of distinct monic linear factors. And when k is odd, what could be ma of x? So, ma of x is x minus 1, is a monic linear factor, x minus 1. And it is minimal polynomial, therefore a satisfies that one. A minus I is 0. That is a is equal to I, a square is equal to I. Thus, whenever a power k is identity for some positive integer k, then a square is I when k is odd. Second case, when k is even. Now, the minimal polynomial ma of x divides xk minus 1 implies ma of x, k is even. When k is even, ma of x is either x minus 1 or ma of x is x plus 1 or ma of x is x minus 1 into x plus 1, the product of distinct monic linear factors. So, it may be this x minus 1 or x plus 1, x minus 1 into x plus 1, that is x square minus 1. So, a satisfies these polynomials, therefore a minus I is equal to 0 either, or a plus I is equal to 0, or a square minus I is equal to 0. A minus I is equal to 0 will give you a is equal to I, then a square is I. A plus I is equal to 0 will give you a is equal to minus I, then a square is I. And a square minus I is 0 implies a square is equal to I. In any case, a square is identity. So, thus if a power k is identity for some positive integer k, then a square is also identity. Thus, option 2 is also true. So far we have proved those option 1, 3, 4 are true. Now we have proved option 2 is also true. That means all the options are true. So the answer to this question is options 1, 2, 3 and 4. That is the detailed discussion of the solution of the problem on real symmetric matrices from the section linear algebra, and it is definitely an important question. I am sure that you have understood the solution of this problem. I request you, if you like my videos, my presentation, my lecturing, if you like these things, please like and share my videos, and please subscribe my channel if you have not already subscribed. And you can share these videos to your colleagues, friends, relatives who are interested in NET examination. I wish you all the best. Thank you.